Hello, everyone. Welcome back. Can you hear me? Malino ba? Okay, good. So today I'm excited to share with you our last activity. It has so many applications, and I hope you can find application for it in your thesis or in your future work. So without further ado, sorry about the dogs barking. And let me share with you my screen and let's go through the activities, skipping through activities, and then we'll have some time and try it out on MATLAB online. Okay. Share screen. Okay. You can also find this in your Uble or your Messenger. Yeah. Okay. Can you confirm if you can see my Word document? Yep, thanks. Okay, let's go through this. So our last activity is on Fourier transform properties and applications. Okay, do you know that the Fourier transform can act as a lens? It can be a model for a lens. Okay. But first of all, the properties, or rather the definitions. Now, the Fourier transform states that any image or signal, Fourier theorem, sorry, can be expressed as a superposition of sinusoids, any signal at all, even images. The Fourier transform is a linear transform that recasts information using sinusoidal basis functions. FT converts a signal with physical dimension x into a signal with dimension 1 over x, which is why if you have a time signal, 1 over time is frequency. But if you have a space signal, x becomes 1 over x, or spatial frequency. Okay. Thus, the FT of a signal gives the spatial frequency distribution of that signal. So the FFT of an image, say our image is given by G, X, Y, is given by capital G, Fx, Fy, equal to a double integral with the function g of xy in there, multiplied by the kernel x e to raised to the minus I2 pi times f sub xx plus f sub yy, and the integration is taken over dx and dy. All right, here fx and fy are the spatial frequencies along the x and y respectively, and an efficient and fast implementation of FT is the fast Fourier transform algorithm, or FFT, by Cooley and Chuki. And so powerful and useful is the algorithm that all signal image processing software, even Excel, have FFT routines among their functions. In MATLAB, the function call is FFT for 1D signals and FFT2 for 2D signals. And it also has FFTN for ND signals. All right. When you use the discrete, so this is known as the discrete FFT, no? When you use the discrete FFT or FFT2, it has the following properties. Based on the Cooley-Chuki algorithm, no, the reason why it's very efficient is because of bit reversal. You can actually flip some numbers and then you can reduce these numbers, which is why the FFT is most efficient and accurate if the image size is the power of 2, meaning if it's 64 by 64, 128 by 128, 256 by 256, etc. And sometimes even if the image is not of this size, it can be zero padded, okay? or padded to make it up to a size that is a power of 2. But sometimes this is automatically done within MATLAB itself, or rather the function itself. Now, the output of FFT2 has quadrants along the diagonals interchange. So suppose an image is a matrix, you can think of it as having 4 quadrants. So, and you call these quadrants 1, 2, 3, 4 in a clockwise fashion, no? The FFT, when you calculate it, comes out with the diagonal quadrants interchange. And so we just have to use the FFT shift function to interchange the quadrants back. The center of the matrix then becomes the origin, or the place where Fx and Fy are 0. Okay. And all FFTs are symmetric. So in FFT2, the quadrants 1 and 3 and 2 and 4 are symmetric. So they are mirror images of one another. The output of FFT is a complex number array. Di ba nga? Kasi may I dito sa equation 1. Kaya since this is a complex function, then G will be a complex function as well. It's a complex number. You can view the real and imaginary parts separately, but to view the intensity, you combine the imaginary and real parts into modulo or use abs to do that. So this abs function automatically converts a complex number into its modulo, okay? Or square root of the real squared plus imaginary squared. By the way, mahina ba yung boses ko or sakto lang? Okay lang? Okay. Okay. Tapos, because the FFT, if you go back to your optics and recall that a lens does, in a way, parang sinushorten niya yung Fraunhofer diffraction. And the Fraunhofer diffraction is essentially an FFT. And remember, di ba, pag may lens ka, form ng image yung lens, pag naglagay ka uli ng lens in front of that same focal distance, babalik uli yung image ng lens, ay babalik uli yung image ng object, but flipped. Okay, so the inverse FFT is just the same as the forward FFT with the image inverted. There is an inverse FFT. So if you have forward FFT given a function in frequency space, you use inverse FFT and you can get the function back in spatial coordinates. Okay. Now, we have 1D FFT and 2D FFT. Unique to 2D FFT as compared to 1D FFT is the fact that the rotation of the image results to its rotation, the rotation of its FT. By the way, can I ask one of you to be a co-host para pag may pumapasok, ipaki-enter na lang sila? Hindi ko makita na pag nagsasalita na ako. Okay lang ba? Jean Michael, pwede ba kitang gawing co-host?
Yes, ma'am.
Ikaw na lang magpa-admit ng mga mapasok. Hindi ko makita yan pag nagsasalita na ako. Wait lang, paano ito? Saan nga ba yung make co-host? Make co-host. Ayan, sige. May pumapasok pa, paki-admit. Alright. Okay, so review muna natin yung mga FFT ng mga common signals. Dalawang common signals na napaka-importante for our application is yung constant. Okay? Okay, pag imaginein mo, if you express a constant in 2 dimensions, g of xy is equal c. Yan na yung equation yan. Okay? Now, pag in-FFT mo ang constant, technically, ang constant, flat lang yan. Walang frequency, walang waves. No? So, essentially, its FFT is the Dirac delta at fx, fy. No? So, when fx equals 0, fy equals 0, then there's a peak. And that's the origin at the origin. Easy, no? Another function that is very important to remember when the FFT of is the sinusoid. Now, so in a 2-dimensional plane, a 1-dimensional FFT is given by equation 2. G of xy is equal to a sine 2 pi f naught, where f naught is the frequency of that sinusoid. Uy, di ba ito yung exercise nyo dun sa first first activity? Ngayon, if you do the math, again, if you apply equation 1, both on the on the constant and on a sinusoid, you can calculate that the FFT of a sinusoid will have this result. Capital G fx fy will have Dirac delta, will have Fourier transform, which are Dirac deltas along the x, fx minus f naught, no? So there would be a Dirac delta here, fx equals f naught with an amplitude of a over 2, and another Dirac delta at, sorry, fx to may kulang ng fx. Okay. Fx plus f naught, no? So of fx equals minus f naught, meron uling Dirac delta with an amplitude of a over 2, and each of them are multiplied by a Dirac delta along 0. Okay, y. So ibig sabihin, this will just be two peaks in the two-dimensional, two symmetric peaks along the fx axis, located at minus f and f naught and plus f naught. Okay, all right. Okay, moving on. Because the Fourier transform is a linear transform, it obeys the convolution theorem. So recall that when you do the convolution of two-dimensional functions, say f and g, no, it's given by equation 4. So transform the uh, uh, variable of f into a dummy variable x prime y prime. Okay, where and ganun din gawin mo sa G, transform its xy variables into x prime, y prime. Pero if you flip mo, you will mirror it. That's why there's a minus sign here. And then this variable xy will be a certain shift, no? A certain shift along x and along y. Okay, given a certain shift x and y applied to G, do this product, do this integration along dx dy prime, mawawala yung dependence on the prime variables and may iwan yung dependence on the unprime variables. Okay? And this is the convolution. Now, I suppose you've heard of the convolution in previous subjects. I would think that it was taught in 165 and some other subjects. Very important function. The shorthand notation for convolution is this cross with a circle. So we can write this long integral as equation 5, f convolved with g. Now, again, convolution is a linear transform or linear operation as well, which means that if f and g are recast by linear transformations, such as the Laplace or the Fourier transform, they obey the convolution theorem, which is, if you take the Fourier transform of h and f and g, their convolution, the convolution of f and g in Fourier space is this, satisfies this, no? Take the Fourier transform of small h, you get h. It's the product of the Fourier transform of f and g, okay, is equal to the Fourier transform of the convolution of f and g. Okay? So kung mahirap man gawin ang convolution in xy space, madali siyang gawin in Fourier space kasi multiplication lang siya. Pero mo yun, i-Fourier transform yung x, i-Fourier transform yung g, tapos multiply mo lang silang dalawa element per element. Ayos. Yung h na yan, pag in-inverse Fourier transform mo, convolution na yan ng dalawa. Napakadaling gawin. And in fact, yung mga convolutional neural networks or convolution na na operations actually do this shortcut para mas madaling gawin itong convolution integral or summation na ito. Okay. The convolution is a smearing of one function against another such that the resulting function h looks a little like both f and h. Remember, convolution, keyword is convolute. Convolute, pag hinanap niyo sa dictionary yan, it means distort. Okay? So that's why the convolution is a parang distortion function. F becomes distorted by G. Okay? And ang result is medyo kamukha ng F, kamukha rin ng G. Yung resulting signal would come out looking a little bit like F and a little bit like G. All right? It turns out this is exactly what happens when you use an imaging device, guys. Kasi imagine niyo, kunyari, ang G is yung original, or rather, this is interchangeable. This is also a property of the linear transform. These two are interchangeable. Pareho lang ang result kapag G is convolved with F. Sabihin natin yung F ay yung object. Kunyari, star. Tumitingin tayo ng isang star out there, galaxy. G can be the point spread function of our camera or telescope. Okay. What we observe is an image. So, tandaan nyo ha, magkaiba ang object sa image. We are trying to image an object using a device, a telescope. All devices will distort the object that we are seeing. So if you think of G as the point spread function of the telescope, what we will see as the image of the star would be H. if the original object, which is the star, convolved with the telescope's point spread function, G. And then what we observe is this H. No? Naalala niyo yung James Webb Space Telescope, guys? Okay. Imagine niyo, kaya niyong i-model yung point spread function niya after this exercise. Okay? So as I said, convolution is used to model the linear regime of instruments or detection devices, such as those used in imaging. For example, in imaging, F can be the object, G can be the transfer function or the point spread function of the imaging system. Their convolution, H, is then the image produced by the detection system, which in general is not 100% identical to the original object. Okay. So with the digital camera, the transfer function is mostly due to the finite size of the camera lens, and the finite lens radius means that the lens can only gather a limited number of rays reflected off an object. Therefore, the reconstruction of the object is never perfect. Right. Okay. Meron ding tinasabing rotation property ang FT. No? So here we have an example. So I want you to follow through. So in this first few processes, this is how you apply an FT. So perhaps this will look familiar to you kasi parang exercise natin to, activity 1. Gagawa tayo ng one-dimensional sinusoid. A two-dimensional sinusoid pero in one dimension lang siya nag-wave. So along the X. So we apply this code in, say, MATLAB. Ganito mag-Fourier transform. Aba, tawagin mo na. Kunyari, so Z yung ating two-dimensional sinusoid, sin 2 pi fx. If ft2z, that's it. Tapos i-abs mo yung FC, remember, para makuha natin yung modulus. Tapos i-interchange mo yung quadrants nila, FT shift. And voila, you can do that. Okay, so I'll head on over to, para lang masimulan natin, let's have a short demo in MATLAB online. You can follow through with me. So if you have MATLAB offline, you can do this. Turn on your MATLAB. Wait, where's my MATLAB online? There. Wait lang ha. Sasagal muna ako ng mga tabs. Cha. Wait. Okay, so let's go to MATLAB online. Okay. Now let's you can click this if you're logged into your MATLAB. Go ahead and click this menu icon here and choose MATLAB online, and let's work on that. Okay. Gawa tayo ng bagong script. Okay. Tapos, copy-paste natin yung nakasulat dun sa lecture. Control C. Yan. Right? So, bigyan ko nga ng pangalan to. Save. So, essentially, gumawa lang tayo ng sinusoid. Tingnan natin. Run natin tong section na to. Ano mo ng section na to? Run natin. Ay! Joke. Bakit ayaw niya? Ayaw na mag-run ng run section pala. Run section. So we're supposed to find 2D sinusoid. Meron bang error? Show up. Yun. Okay. So ito na yung ating 2D sinusoid. Okay, so please remember, this is a synthetic signal. That's why there's a 1 and a -1. Tandaan, pag real image, walang negative values. Okay, FFT na natin siya. It's very simple, guys. Masyado bang maliit? Liliitan ako sa ating... Dali ano ng preferences dito? Ngayon, preferences. Oh, preferences. Ang liit eh. Yun. Ilakyan ko lang yung font. Ay, font. And 14. Yon. Okay. Okay. So FFT, simple. FC, tawagin natin siyang FFT of Z is equal to FFT2 of the function Z. Okay? Tapos, pag i-display na natin siya, tatandaan na una muna, kailangan natin i-abs ang kunin yung modulo. Pangalawa, kailangan nating i-FFT shift siya para magmukhang yung gitna ay the zero frequency. Mas intuitive pag ganito, guys. And of course, bigyan natin siya ng variable name, FC mode. Okay. And now, we can go ahead and create a second figure and display this as, once again, a mesh. This time, ano na siya? Hindi na siya real imaginary dahil inabs natin siya, right? So, tingnan natin. Ini-expect natin na pag sinusoid na ganito, we expect 2 dots, no? Hintayin lang natin. Ay, nga pala. Run section. Ito, run natin ito section na ito. Click. Hintay. Ayun siya, di ba guys? Yun, dalawang Dirac delta, no? Dalawang Dirac delta. Ini-expect natin yan na dyan lang. Okay. Yan, no? Kasi remember, di ba yung sinusoid ay pa ganyan-ganyan, no? So imagine niyo of course, pag change ko to into y, for example, yung dalawang Dirac delta naman to will appear along the y-axis, right? All right. So, balik tayo dun sa ating lecture. Okay. Okay. So essentially, yun yung ginawa natin. Now, you change the frequency, play with it, change the frequency, and discuss what happens to the FT. So, bago-baguhin nyo tong F and see what happens, no? Now, ito na yung sinasabi ko. Digital images have no negative values. Simulate a real image by adding a constant bias to the sinusoid you generated in step 1, no? Take the FT and display. So, what do you observe? Gawin natin kaya yun. Now na. Okay. So, maglagay lang tayo ng constant bias dito. Let's say, let's put, I don't know, 5. Okay. So, i-run natin siya ulit, itong section na to. Run section. Baka mapatungan niya itong figure 2. Hindi pala na-change yung figure 2. But, yan. Patungan niya yung figure 2. Notice na hindi na siya sa negative 1 to 1. Instead, nasa plus 4 to plus 6 na siya. Okay. And real images would look like this. No? Wala siyang negative. Wala naman negative sa image. Yeah? Hello?
Hindi po kita yung MATLAB. Are you showing MATLAB po?
Ay, oo. Thank you. Hindi pala ako nag-share. O nga pala. Wait lang. Iba yung na-share ko kanina. Thank you for telling me. Wait lang. Stop share. Thank you. Share screen. Okay, this one. Okay. Okay, as I was saying kanina, ang ginawa ko, ito guys, dito sa part na to, lagyan mo lang plus 5. Tapos nung rinan ko, ayan na siya. Ito na. Okay? Naka-elevate na siya. Hindi na siya from -1 to +1. Naging +4 to +6. And images, actual images are like that. Walang negative intensity ang images. No such thing as a negative intensity. Alright. So, ano nangyari dito guys? Remember kanina, no? Ang Fourier transform ng constant, Dirac delta. Ang Fourier transform ng sinusoid, dalawang Dirac delta, symmetric about 0, at yung location niya depends on the frequency. Okay? Right? O ngayon naman, ano yung FFT nito? Kasi ganito ang representative ng real actual image data. Press natin yung run section. Nandito na ako sa pangalawang part, no? So papatong dito yung Fourier transform. Okay. Okay, dahil doon sa constant na yon, nagkaroon ng pangatlong peak. Kita niyo yon? And yung peak na yan ay nasa gitna. So ito, never mind these axes here. When you do actual Fourier transform na proper, this should be replaced by physical frequencies along x and y values. But right now it's in matrix form, so these are just matrix indices. But imagine nyo na ito yung origin in frequency space. And so, remember, a constant, the Fourier transform of a constant is a Dirac delta at 0 frequency. So that's why nung nag-add tayo ng constant kay sinusoid, ito yung itsura niya. Merong isang peak na mataas at may dalawang malinggit na peaks sa gilid niya corresponding to the sinusoid. Now guys, this is very important. Tandaan niyo palagi ito, may insight yan. Tapos dyan. Tayo ng figure 3. Display natin tong image natin na to as, itong 3D mesh image natin na to as an actual image. Now you can use image SC and let's see if it works, no? I-display ko to ng top view ng parang intensity image, no? So here, do you see the command line? I just wrote, FC mod. This is the Fourier transform. Okay. Okay, just wait and here it comes. Okay. Pag image na ang ginagamit nyo at pinu-Fourier transform nyo, baka ito yung makita nyo, parang wala. Pero sa totoo lang, kanina, alam natin na ganyan yan. No? Bakit ganon? Nasa pawan ng DC. No? Yung intensity ng DC, itong gitna na to, that's the DC frequency. DC frequency. That's the Dirac delta for the DC signal. Yung meron sanang dalawang dots dito, hindi makita. Right? Okay? Tandaan niyo yan, ha? Real images would be like something like that. May constant bias, walang negative parts. Now, balik uli ako dun sa sa lecture ko. Stop share, balik uli sa paki-remind na lang ako, nakakalimutan kong i-share yung appropriate screen. Ito na. Okay. Yan. Okay. Ito, 4. Digital images have no negative values. Simulate a real image by adding a constant bias to the sinusoid. Yun ang ginawa natin. Take the FT and display. What do you observe? So, saan ba natin magagamit to? Suppose you took an image of an interferogram in a young double slit experiment. Nagawa niyo no? Kayo ba tayong... Guys, may tanong ako. Kayo ba ay ever nakastep na sa NIP physically? Di pa, no? Tama ba? Anong year nyo na ba? Second? Third?
Third at fourth po, ma'am.
Fourth. In your 4 years, nakapasok na ba kayo sa NIP? Nakagamit ba kayo ng laser, etc., any equipment? Are you familiar with the Young's double slit experiment?
Yes po, ma'am.
Yung may double slit na aperture, you shine a laser behind it, you look at the diffraction pattern from far away, and what you will see would be a sinusoid. Right? Tapos, what you can do is you can take a picture of that sinusoid, right? And then you analyze that picture and do image processing. But what would happen would be, that's called an interferogram. But what can you do to find the actual frequency? Remember, walang negative ang intensities, no? Ang images. So suppose a non-constant bias is a sinusoid, how can you get the frequencies of the interferogram, as I said? So the trick here is to remove that bias, So for example, let's regenerate this image. Itong figure 1 was the original image where we have -1 to +1. This is the ideal case. So how do you get back to this? Simple. Find out what the constant bias is and subtract it from your interferogram signal. Find the constant bias. And how do you find the constant bias? Well, one way is you just get the average. When you get the average, you have an idea what that the average value is when you mean center it. So the average is the mean, no? So when you subtract the mean, it's mean centered. You have equal parts, may positive parts, may negative parts. Ma'am, wala po ulit. Oh, thank you. Thank you. Sorry. Okay. Sorry. As I was saying, have a look. Ito yung original, yung unang-una natin ginawa na sinusoid. Look, -1 to +1. Ito yung ideal case, no? Para ma-detect natin yung dalawang peaks ng sinusoid. So, paano kung image na ng sinusoid ang tinitingnan natin? The key is to subtract that constant bias. How do you get that constant bias? One way is to get the average, no? Average intensity. So, but kung may average intensity, iyon ang isubtract mo sa signal. So, again, let's do this. Remember, ang FFT nito ay hindi makita dahil nasa pawan ng DC signal dyan. Pero sa totoo lang, meron yan. Ang gusto nating makita yung information about the sinusoid. Every time you see two peaks na symmetric about the center, that is a sinusoid, guys. Okay. O sige. So, kunyari, generate natin to ulit. Okay. Okay. Tingnan nyo ha. Magiging +4 to 6. O yan na. Okay. So, mukha na rin oh, by the way, pwede rin natin tong pakita as an image, no? So, mukha na siyang real double slit image. So, figure 4. Ito naman, image SC, display natin siya as an intensity image. Ayan siya. Okay? Alright. So, kita natin may peaks and troughs, no? Okay, next. Okay. So, kunin natin yung average nito. Let's get down. Okay. Okay. Kunin natin yung mean. Mean. Parang dalawang beses natin kunin yung mean. Z. Ano kaya ito? 5. Okay. Bakit dalawang beses ko ginawa yung mean? Kasi two-dimensional to eh. So, you get the mean along X, you get the mean along Y, or you can also do a double application of mean. If you only do a mean Z, ito yung mangyayari. A bunch of numbers will appear. Okay? Ginagawa niya kada column, kinukuha niya yung average. Okay? So that isn't helpful. But if you mean and mean it, ibig sabihin, i-average niya itong mga column values na to. So you're left with one number, mean. Okay? And therefore, when you do C minus, so let's create another figure. Figure 5. So yun na, di ba? Mesh Z minus mean of mean Z magiging negative na siya. Matatanggal na yung constant bias, and then you can do the FFT without the overpowering, ayan, yung mga minus 1 to 1, without the overpowering DC signal. Okay? Okay? Alright, stop share. Now, why do I emphasize this so much? Kasi gagamitin nyo yan. Balik tayo sa share screen. Sana hindi kayo nahihilo dito sa change nitong aking screen. Okay. Alright. Dahil application yan, guys. Sige, ha? By the way, try nyo to. Pwede nyo ring i-rotate yung sinusoid nyo. Pwede ka ring mag-add ng different sinusoids together. Okay? So, I have done already up to step 4. You do step 5, 6, 7. Okay? And then you do this anamorphic property of FT. Ito lang ipapakita na anamorphic means pag mataba sa isang space, mapayat sa opposite space. Okay? Kasi 1/x nga yung dimension ng Fourier space. So, tignan nyo. The center is 0 frequency. So, if you're close to the center, that means you have low frequency. The farther you are from the center, that means that you have higher frequency. Okay? Now, tingnan mo naman, kunin mo yung FT ng different types of patterns, okay? Like a tall rectangle. Iba kung gumawa kayo dati ng square aperture or whatever. So here, try and make rectangles or ellipses. Basta yun, yung iba yung dimension niya or haba niya along along X versus along Y. And look at the FFT and you will see that it will be anamorphic, meaning pag mataba siya sa isa, mapayat siya dun sa isang dimension. All right. Now, let's use this newfound knowledge of ours in applications. Filtering in Fourier space. Unwanted repetitive patterns in an image can be removed by masking their frequencies in the Fourier domain. Alternatively, desired frequencies in the image may also be enhanced. Okay. We can create filter masks to block out unwanted frequency. In creating a filter mask, careful consideration of the convolution theorem is necessary. Remember that the FFT of a convolution of two functions in space is the product of the two functions as FFT. Okay? And the convolution of a Dirac delta in a function f of t results in a replication of ft in the location of the Dirac delta. Okay. All right. Makikita niyo to here, no? Itong number 2 will be found here. Create a binary image of 2 dots, 1 pixel each along the axis symmetric about the center. Take the FT and display the modulus. Replace the dots with circles of some radius. Discuss what you observe in the FT modulus as you vary the radius. Of course, if you have 2 dots, 1 pixel each, symmetric along the x-axis, parang dalawang Dirac delta yan, ano? So pag in FFT mo yan, you expect, what do you expect? Okay, you might expect a sinusoid, right? Kasi interchangeable yan eh. If in space you have 2 dots symmetric about 0, if you Fourier transform that for certain, mukha siyang sinusoid. Okay? Whereas sinusoid in space would be a 2 Dirac delta, 2 dots in Fourier space. So interchangeable yan. Now, instead of dots, you replace the dots with a circle of some radius. Then FFT mo uli yan. Discuss what you observe in the FT modulus as you vary the dots. Replace the dots with square of some width and discuss what you see. Now, ito. Create a 200 by 200 array of zeros. Put 10 ones in random locations in the array. Okay? Spread ka ng, magkalat ka ng ones kung saan doon sa array na yun. These ones will approximate Dirac deltas. Kunyari, stars, no? Kunyari, ito nga yung mga, kunyari, gawa tayo generate tayo ng artificial stars. Call this array A. Now, create an arbitrary 9 by 9 pattern. Bahala ka kung anong ilalagay mo sa pattern and call it D. And convolve A and D. What do you observe? Okay. Now, create another 200 by 200 array of zeros, but this time put equally spaced ones along X and Y in an array. So para siyang grid. I think gumawa rin kayo dati ng grid, ano? So exercise natin, parang pixels yung ginawa natin. Ito naman, parang ano lang, equally spaced ones. So para siyang points na equally spaced in a grid pattern. Change the spacing of the ones and repeat. Importante ito. So have a look at the FFT of this grid. Okay. Now, the insight, guys, that you will get out of this exercise, you will apply in 2 applications. So, lunar landing scan pictures, line removal. Okay, nung nagsisimula pa yung space exploration, so nagpapadala sila ng spacecraft sa moon, tapos ini-explore nila kung saan ba pwedeng posibleng mag-landing. They were the first ones, the astronauts were the first one to carry a digital camera. Yun yung unang time na nagkaroon ng digital camera at dinala pa sa moon. Now, digital cameras are so ubiquitous, but nung panahon na yon, it was only for research and research grade ang level niya. They carried the digital camera and captured images of the moon, but they had to stitch that. There was a time that bago pa digital camera, they had to develop the image and then stitch also the images as well, no? And because of the stitching, nagkaroon ng parang repetitive line patterns dito kung saan yung seams, kung saan sila dinugtong-dugtong. Do you see that? Okay? Diba? May nakita kayong parang repetitive line patterns yan. Yeah? Right. The 2 groups of irregularly shaped craters north and west of the landing site are secondaries from the Sabine crater. This view was obtained by the unmanned lunar orbiter B spacecraft in 1967 prior to the Apollo missions to the moon. The black and white film was automatically developed on board the spacecraft and subsequently digitized for transmission to Earth. The regularly spaced vertical lines are the results of combining individually digitized framelets to make a composite photograph, and the irregularly shaped bright and dark spots are due to the non-uniform film development. So, in this case, film paling gamit nila. Later, digital cameras na yung dala-dala ng mga astronauts. But this, man pala to, this was film pa, no? Negatives pa. Tapos dinigitize doon and then sent to Earth. And ang result, merong artifact na repetitive lines yung yung composite image. Okay, remove the vertical lines in the image by filtering in the Fourier domain. Paano yun? This. Okay, anong gagawin natin? Ang strategy natin. For sure, pag may nakita kang repetitive something dyan, for sure may makikita kang mga peaks. Okay? May mga symmetric peaks. And that would correspond to the sinusoids or the signs that are present because of these repetitive patterns. And you want to block that out, guys. So it's in the Fourier space of this image, i-block out yon. Oh, by the way, to make sure of the location, anong gagawin? Kunin yung average value, average intensity nitong image na to at isubtract doon sa original image para may negative and positive parts para ma-enhance yung sinusoids. Okay? So pag tingnan mo yung Fourier transform nitong image na to, check mo kung may nakikita kang peaks or even lines of peaks, no? Okay? Hilera ng peaks. Okay. Filter it out by creating a mask. Multiply that filter mask to the Fourier transform, essentially ones and zeros yung mask. The zeros, if you put a 0 there, that means any pixel multiplied to it will also become 0. So that's what I mean by filtering. Okay. Okay, another application, canvas weave modeling and removal. Okay, here is a image, part of an oil painting that we scanned in Vargas Museum. Remember, research ko sa art din, so we scanned several images and may time na kailangan naming aralin yung brush strokes ni Amber Solo. Kaso mo, may mga paintings na mas litaw yung canvas weave nila, guys, no? Medyo nakaka-distract doon sa kailangan naming gawin. Can we remove this? Total, mukhang repetitive naman tong canvas weave patterns eh. Yes. So again, Fourier transform nyo to, guys, and check nyo yung Fourier transform kung may makikita kayong mga dots in symmetric locations and try to filter them out. Again, gagawa kayo ng blank image, same size as the image here, all ones. Tapos, isi-zero nyo lang kung saan may nakikita kayong, i-convert nyo lang to 0, yung pixel na yon na kung saan, dun sa location na yon may nakikita kayong peaks. Okay, may peak, and that would correspond, symmetric peak, that would correspond to a sinusoidal pattern. Yeah. So are the brush strokes, so once you inverse Fourier transform that, no? So imagine niyo no, so nag multiply kayo, Fourier transform. Steps are Fourier transform this image. Oh, by the way, subtract again the mean. Okay, Fourier transform it, find the peaks, create a mask to zero out the peaks, multiply that mask to the Fourier transform, inverse Fourier transform, and you get back to the original image. Hopefully, minus the peaks. That is what filtering is about. Okay, are the brushstrokes in the painting enhanced? Invert the filter mask. Zeros become 1 and vice versa. So, imbis na remove or in-erase natin yung mga peaks, sila yung in-enhance natin. So, 0 lahat except for those peaks. Now, take the inverse Fourier transform and observe the generated modulus image. Is it close to the appearance of the canvas wave? So, kumbaga, we can do either way. We can either, if we want to study the canvas wave, we can enhance these repetitive patterns, or if we want to study the painting minus the canvas wave, we can filter out these repetitive patterns. So that's one application. Okay, simulation of an imaging device. So as I said, you can simulate what a telescope or what a microscope can see given using the Fourier transform. So generate muna tayo ng artificial image, kunyari NIP, no? You can use paint, type NIP, large fonts, no? And let it fill 50% of the space. This represents your object, and note the edges of a sans serif font are sharp. Okay. You might want to save this as bitmap. Huwag JPEG ha. Pag ginawa nyo to sa paint, don't ever use JPEG. Magkakaroon ng artifacts yung edges. Okay. Now create another 128 by 128 image of a white circle centered. Okay. You know how to do that, no? You know how to make synthetic images. Okay. Open both images in MATLAB as grayscale images. For example, this way. Okay. Convert them to gray. All right. FFT shift one of them already. Okay. Kasi in this, what we're going to do is we're going to do an imaging simulation. Okay. The aperture is already in the Fourier plane and need not be FFT. So the circle actually is a model of the aperture of our imaging device or the lens. So ito yung circle, ito yung aperture, ito na yung model ng imaging device. And then i-F15 natin siya. Ang gagawin natin is i-convolve silang dalawa in the Fourier space. Get the product of their FFT and get the inverse to get the convolved image. Okay? As I said, yung circle, iyon na po yung iyon na yung pinaka-FT version or model ng ating So hindi na natin siya kailangan i-Fourier transform, bagkus or automatically i-multiply na siya. Kumbaga it's in the Fourier space na pag gumawa tayo ng circle as a model of the aperture. Tapos i-multiply lang natin sila element per element with FFT of the NIP image. Okay? So, tapos i-inverse FFT lang natin. You can use FFT2 again or IFFT2. Okay? Bakit FFT2? You can actually use IFFT2 as well. Okay? And then, i-display lang sila. And compare the original NIP and the imaged NIP for different radii of the white circle. Discuss the effect of the aperture lens and the quality of the image. So this exercise naman is a bit of optics kasi isi-simulate nyo anong effect ng aperture, size ng aperture dun sa quality ng image na produce na. Okay? So, correlation. The correlation between two-dimensional functions f and g is given by parang convolution integral, guys. Ang kinaiba lang, naging positive yung negative dito. Okay? Shift pa rin. But in the opposite direction. In shorthand notation, parang ganyan yung symbol for correlation. Okay. Dahil kahawig siya ng convolution integral, well, ang pareho silang sila if you do this, no? The convolution and correlation are equal if you have you mirror f and then you take its conjugate and then you convolve. Okay? where the superscript asterisk means complex conjugation of F. So, ibig sabihin yan, pag symmetric naman yung F at real function naman siya, eh, parang it's just the same as f of x, y lang. Similar to the convolution, there is a correlation theorem which holds for linear transforms of f and g. Okay, so the correlation, pag kinuha mo yung Fourier transform nitong tatlong to, P, F, and G, pag kinuha mo yung product ng big F, Fourier transform ng F, complex conjugate mo siya. Multiply mo element by element dun sa Fourier transform ng G. Yung product nila ay yung Fourier transform ng correlation. Yun. Tapos pag in-inverse FFT mo tong P, ayun na yun, na-correlate mo na yung F and G together. Okay. The correlation P measures the degree of similarity between two functions F and G. Kanina, yung convolution smearing. Dinidistort ng F yung G or vice versa. Dinidistort ng G yung F. So yung resulting image H is a distorted version of both. Magkamukha sila pero parang may halo ng F, may halo ng G. Ito namang correlation, guys. So kinaiba niya, ganyan, ano? Ang hinahabol niya naman is kung magkahawig ba sila. Okay? The image that will come out after you correlate would be, hindi siya mukhang image, mukha siyang peaks. Nagpipeak siya, tumataas yung value niya pag saktong-saktong kamukha ng F, yung G, dun sa location na yon. Okay? So the correlation P measures the degree of similarity between two functions F and G. The more identical they are at a certain position, X, Y, the higher their correlation value. Therefore, the correlation function is used mostly in template matching or pattern recognition. So an important consequence of equation 9, is that if F or G, if any of them are even functions, the correlation is equal to the convolution. Okay? So, ito, pattern recognition tayo using Fourier transform. Template matching using correlation. Okay, template matching is a pattern recognition technique suitable for finding identical patterns in a scene, such as in the case of finding a certain word in a document or a certain symbol. So type in the following text in a 128 by 128 white background using paint. The rain in Spain stays mainly in the plain. Create a 128 by 128 image of the letter A using the same font and the same size as the image in step 1. It has to be the same font and same size. Ano? Put the A in the middle of that blank 128 by 128. Open both images in MATLAB as grayscale and get both their Fourier transforms. Element per element, multiply the FT of A and the conjugate of FT of the text image. The way to conjugate that is conj. There's a conj function to get the complex conjugate. Compute the inverse FT and display the output. Explain the meaning of the output obtained. And element per element, multiply. Sige, so essentially, pinerform natin yung, by step 4, pinerform natin yung correlation. And then you will observe the image by inverse FFT, the output in step 4. And what do you expect? You should expect that there would be high peaks where the pattern, the target pattern, coincides with the test pattern. Okay. Lastly, edge detection using the convolution integral. Edge detection can be seen as template matching for an edge pattern with an image. So create a 3x3 pattern matrix of an edge using the edge such that the total sum is 0. So for example, here's a 3x3 pattern. Pag tinotal mo yung sum nito, 0 siya. Or variance in other direction. In MATLAB, this can be called by creating a matrix like this. Now, convolve this image with the NIP image. You can use conv2. If hinukay mo yung conv2, essentially it uses FFT. Pag inopen mo itong conv2. So anyway, the shortcut is conv2. It does convolution using FFT. Try the other direction patterns such as vertical, diagonal, or even try a spot pattern like this and comment on the convolved image for various patterns applied to NIP. It's a long one, but this has many uses. This will give you terrific insight on the uses of FFT. And I hope you do work on this diligently in this because you might find use for it in your future research. Okay, I'll stop share here. And do you have questions? Now, we still have, I think I still have one session on Friday. Is it so? Can't remember. But if you have any question at all from the past three, this is the last activity for this module, by the way. Okay, just do what some of your classmates did. Message me, and I can initiate a tutorial. Okay. Okay. Any questions about that exercise, that last exercise? Once, going twice. So done. Okay. Since I don't see any question right now, I assume you're still thinking about it. I will wait for your questions in the messenger or other avenues like email. And that's it for today. Okay. All right. So this has been Maricar Soriano, your IPL 157B module instructor, and I'll see you. Thank you. Class dismissed. Bye.
Thank you, ma'am.